the empirical rule states that if data is normally distributed, that 68% of our, or about 68% of our data will lie within one standard deviation on each side of the mean. 95% of our data will lie within two standard deviations on each side of the mean, and 99.7% of our data will lie within three standard deviations on each side of the mean. We're going to take a look at that idea along with what a z-score is and how we use z-scores to come up with probabilities in this lesson. So to do this, I'm going to use a constant example here. We're going to use the same example for all these problems, and that's IQ scores. IQ scores are approximately normally distributed, and the average IQ score, the mean, is about 100, and the standard deviation, which is a typical difference from the mean, is about 15. So based on that concept and the empirical rule, that says this is 85. One standard deviation below the mean. This is one standard deviation above the mean, which is 115. That says that about 68% of people have an IQ score between 85 and 115. Okay, so we're going to use that idea a couple of times here, along with learning some things about z-scores. So here's an example. What is the probability of a randomly selected person having an IQ score higher than 130? Well, we said earlier that this is 100, the mean. The mean's right in the middle. This is 115, this is 130. So 130 is two standard deviations above the mean. And we're trying to find the probability of getting a score higher than that. So we're trying to find this part of the curve, which we can tell is less than half of the curve, so it's going to be less than 50% or less than 0.5. Well, we can use the empirical rule to get a better idea. We know that based on, again, the empirical rule, 95% of our data lies within two standard deviations on each side of the mean. So everything under the curve has to add up to 1 because that's 100% of our data. So we have 5% of our data lies in this tail and in this tail combined. Since it's perfectly symmetric, half lies in this tail, half lies in that tail, or in each two tails. So basically half of 5% is 2.5%, or as a decimal, 0.025. That's our approximate based on the empirical rule of the probability of getting someone who has an IQ score greater than 130. It's an approximate. Now we can get a better answer by using something that we call a z-score. Now what a z-score is how many standard deviations above or below the mean is. 130 is 2 standard deviations above the mean. So our z-score is 2. So we're going to take a look at a z-table now. Notice I'm going to the positives. We'll take a look at z equals 2.00, which is we're exactly 2 standard deviations above the mean. This is the whole number, the tenths number, and this row tells us the hundredths decimal. So we're looking for this right here, 0.9772. Now, that is the probability. Notice it says left tail area. It will always give us the area or probability to the left of that score. So that means basically 97% of people have an IQ score less than 130. So let's get to the left. So if we go back to our, this says that everything less than this score is 0.9772. So if we're trying to get the probability of being greater than that, we can subtract it from 1 since we know the curve adds up to 1. So 1 minus 0.9772 is 0.022. 0.28. And notice that that's pretty close to what we got using the empirical rule. The empirical rule is an approximate, and the using the z-table will give us a more accurate answer. So let's look at another example. This says, same scenario, what is the probability of a randomly selected person having an IQ score 85 or lower? So again, we have our setup. We know 100 is right here. .85 is exactly one standard deviation below the mean. And we're trying to get lower. So this time when we look in the chart and get that probability, in just a second, we don't have to subtract it from 1 because remember the chart gives us the area to the left. Now first let's get an approximate using the empirical rule. We know that this is 0.68. 68% of our data lies within one standard deviation of the mean. If we subtract that from 1, we get 0.32 or 32%. Half of that lies in each tail, so that means 16% in each. So our estimate to our problem using the empirical rule is 0.16. So now let's use z-scores. We know that 85 is one standard deviation below the mean. That's why we have a -1. It's below the mean. So we can go to our chart. Notice now I'm going to get the z-chart negative because I'm looking at a negative z-score. And negative 1.0 is right here. 0.1587. And that is our answer. Close to 16%, which is what we got from the empirical rule from here. And this is a more accurate answer, about 0.1587. That's the probability of getting someone who scores an 85 or less on the IQ test. Okay, so take a look at a few more problems. What is the probability of a randomly selected person having an IQ score less than 120? Well, this is the first time we can't use the empirical rule, because 120 is not exactly 1 or 2 or 3 standard deviations above or below the mean. We know this is 115, this is 130, so 120 lies around here. And we're trying to get the probability of getting somebody that scores that less than 120. So we want the area to the left, this area over here. So can't use the empirical rule this time. So what we need to do is find the z-score. We need to find out how many standard deviations above the mean 120 is. Well, we haven't used the formula yet, but we have a formula for it, but hopefully it makes intuitive sense. 120 is 20 IQ score points above the mean. So I have 120 minus 100 is 20 IQ points above the mean. And since we know a standard deviation is 15, we can divide that by the standard deviation to get how many standard deviations above the mean it is. So that's 20 divided by 15, that's 4/3, which is 1.33. Now that's to 2 decimal places. So we can take a look at our table. Notice our z-score is positive, so I'll go to the positive z-scores. And I'm looking for 1.33, which is, this is 1.3, the whole number in the 10th decimal. So I'm looking at 0.9082. And since we were trying to find the probability of being less than 120, that's our answer. We don't have to subtract from 1. So 120 was here. And that value gave us the probability to the left. Which is 0.9082. So now we'll show you a different way to use a calculator. So we have, turn it on. So if you go to second variables, you get a list of distributions. We're going to use the normal CDF function first. So normal CDF, go to enter here. So if you have an 84, it'll bring up this prompt. If not, I'll show you at the next screen what you should put in. So we need a lower limit and an upper limit, and we're in terms of z-scores. I failed to mention earlier, but the mean of the z distribution, the standard normal distribution, is 0. 0 standard deviations above the mean, that's right in the middle. And a standard deviation is normed to be 1. So if you're using z-scores, then this should always be 0 and 1 here. So now our lower limit, we're trying to find less than 120, which was a z-score of 1.33. So we want 1.33 and less. So our lower limit is really negative infinity, because we want everything less than 1.33. Well, the closest thing we have to negative infinity in our calculator is 10 to the 99th power, the negative value of that. So negative 10 to the 99th power, which is just a very big negative number. And the e, it comes from right here. Second, comma, will give you e. And you just put 99 right after that. Now our upper limit here is 1.33. $120 was basically 1 1/3 standard deviations above the mean, or 1.33 standard deviations above the mean. So now if I keep u as 0 and sigma as 1, and I'll go down to pace. So if you don't have an 84, then this is the screen that you'll be working with anyway. Now we're all in the same boat. We have normal CDF. You have a lower limit. Comma, upper limit, comma, mean, comma, standard deviation. And actually, if you don't even put 0 and 1 here, the calculator will assume that you're working with the normal distribution, the standard normal distribution, and will assume that the mean 0 and the standard deviation is 1. So if we hit enter here, we get the same probability that we got with the table, 0.9082. And actually we get an even more accurate answer because we get more decimal places. So that's another way to do it, to use normal CDF in the calculator. So let's look at another example now. Now we want more than 125. So again, we can't use the empirical rule. Because 125 doesn't lie exactly 1 to, remember this is 100. This is 115, 125 is around here. So we're trying to find the probability to the right. Again, we know it's going to be less than 0.5 because it's less than half of the curve. So we get our z-score. Again, we can work with this formula now, and I'll write it out now. X minus mu, which is the mean, divided by the standard deviation. So in this case, it's 125 minus 100. I'll go ahead and put 25. Divided by the standard deviation, which is 15. So now we have 5/3, which to 2 decimal places is 1.67. and we're trying to get more. So when we look in the table will give us this percentage first, so then we'll have to subtract from 1 to get our answer. So let's look at a table. Again, I'm looking for positive z-scores. I'm looking for 1.67. Which is right here. 1.67, 0.9525. Now again, that's the probability to the left. So we can subtract that from 1. 1 minus 0.9525. Some trouble. That's 0.0475. So that's our answer. The probability of getting someone with an IQ score greater than 125 is about 4.75%, or a probability of 0.0475. So we'll take another look at the calculator. So go back to the second option, normal CDF. This time we're trying to find greater than 1.67. So because we're going to the right tail, our lower bound is our z-score that we found, 1.67. Now our upper bound is basically positive infinity. And the closest we have in our calculator to positive infinity is e to the 99th power. Again, our mean is 0 and our standard deviation is 1 because we're working with z-scores. So now I can paste that. Notice now I will not have to subtract from 1. I'm getting the probability greater than 1.67, so this will be my final answer. And that's what we got, 0.0475. Now I'll also show something else here. If you work with raw scores, and sometimes you're going to be asked or forced to find the z-score anyway, so this won't be as helpful, but it always is a good way to check. You can work with raw scores. So our lower score, we want 125 or greater, so let's call that 125. Now we're working with IQ scores, not z-scores. Upper bound is still infinity, basically. We can't have an IQ score of infinity, but this will take care of all of that right tail. But now we have to change our mean to the mean IQ score, which is 100, and a standard deviation of 15. And then we'll get very close to the same answer. And the only reason we have some difference, this one actually is slightly more accurate because this z-score we rounded to 2 decimal places, and the calculator will round the z-score to how many ever decimal places it holds. Looks like maybe 10 or so. So that's again another example of using the calculator and the z-table. So let's look at another one. This time we're trying to find the probability of an IQ score being between 80. Let's see, this is 85, so 80 is right here. And 115. 115 is exactly right here. And we're trying to find the probability of being in between these two. So we're not going into either tail. We're trying to find this percentage right here. It's hard to tell whether it's greater than or less than 50% based on the drawing that we have here. So what we're going to do is come up with 2 z-scores. We know 115, the z-score is going to be 1. Because it's exactly 1 standard deviation above the mean. We would have 115 minus 100. Tells you that it's 15 IQ points away from the mean. And since the standard deviation is 15, that's exactly 1 standard deviation above the mean. So that's 1 as a z-score. Now we'll find a z-score for 80. We know it'll be negative 80 minus 100 divided by 15. We have negative 20 divided by 15, which is negative 4/3, which is negative, again, to 2 decimal places, negative 1.33. Now first, we'll talk about how we'll get this using a table. A table will only give us the proportion of data to the left, or the area under the curve to the left. So if we use z equals, let me write this, negative. If we use z equals 1, it's going to give us all of the area that's less than 115, or 1 standard deviation above the mean. But then if we subtract the percentage that's less than 80, or less than negative 1.33, we will get the middle percentage here. So that's what we're going to do. Our z-scores are negative 1.33 and 1, and we just want the percentage between those two. So let's take a look at the chart first. I'll need to use both of the z charts at one point. So let me do the positive first. 1 is 0.8413. So I actually go ahead and write that here. 0.8413. And now we need z equals negative 1.33, which is right here. That's the percentage less than IQ score of 80. That gives us 0.0918. 0.0918. So I'll subtract that from our answer. And I'll get that from the calculator. Get that difference. I'm going to leave this here. So we have 0.8413 minus 0.0918. So that's our answer. That's the proportion in between. Almost 75%. Basically 75%. So I'll do 7.7495. Now, there's an advantage of doing this problem in the calculator. If I go to second variables, go back to my distributions. And go to normal CDF. This time I can use put my mean and standard deviation. I'll go back to be 0 and 1, meaning I'm using z-scores. This time, since I'm not going to the tail, I can just put my lower bound in, negative 1.33. And my upper bound of 1. I'm trying to get the area in between these two z-scores, so I have a lower bound and an upper bound. And when I paste these, we get our answer that we had here, 0.7495. We didn't have to subtract anything off because we had a lower bound and an upper bound here. Okay, so take a look at another example. This one's a little bit different. What IQ score would a person have if their IQ was higher than 60% of people? So think about the curve. This person is lower than 50% and higher than 50%. Someone that's to the right of that is higher than more than 50%. In other words, someone that is higher than 60%, somewhere like this. 60% of people are lower than them, 40% are higher than them. So they are higher than 60% of people. So we know that this area is 0.6 and this area is 0.4. So what we're going to do is try to find this actual IQ score. We know it's going to be greater than 100 because 100 is right in the middle. So what we're going to do first, we're basically working exactly backwards that we did last problem. We're going to first find the z-score and then use that to find the x-score, the raw score. Okay, so first we'll use the z-table. We're looking for a positive z-score. We know it's positive, it's on the right side of the mean. And this time we're not looking at z-scores yet. We're trying to find 60% as a probability, or the closest that we can get to 60% as a probability. And this is it, 0.6. So the z-score that corresponds to that is 0.25. So how does that help us? We know that the score we're looking for is basically 0.25 standard deviations above the mean. Well, we know that this formula we've already used. That's mu. And we know mu is 100. We know sigma is 15. And now we know z is 0.25. So we're just going to solve for x. So we know that this score is basically 0.25 standard deviations above the mean. We don't know x. But we know standard deviation and the mean. So this becomes a fairly quick algebra problem. We're trying to solve for x, isolate x. We're going to multiply both sides by 15, then add 100. So that's what I'll do. 0.25 times 15 plus 100. So 0.25 times 15. And that gives us how many how much IQ points above the mean it is. So then if we add that to the mean, we're looking at an IQ score of 103.75. So that's our x value. That's the answer that we're looking for. So another way to look for that, if we go to the same list of distributions, instead of going to normal CDF, we can go to inverse norm. And inverse, you can kind of think of the inverse function. It goes in the opposite order. Instead of you telling the calculator a z-score and it telling you a probability, we give the calculator a probability and it gives us a z-score. So they want the area, and that means the area to the left of the z-score. So that was 60%. So first, if I keep 0 and 1 as my mean and standard deviation, that is 0.25, which was our z-score that we found. Means that's how many standard deviations above the mean it is. Now, similar to how we did with normal CDF, I can also do 0.6. If my mean is 100, now I'm working with raw scores. Standard deviation is 15. Still, 60% is to the left of this score. Now if I paste it, I'm going to get that score, 103.8. So that's the IQ score that is higher than 60% of people. I think we have one more example. Yep. So the last one says, what two IQ scores would make up the middle 50% of scores? Well, we remember that 68% of our data lies within one standard deviation. Now, this is if we the middle one standard deviation is going to be 68%. So if we're looking for 0.5 in the middle, that's going to be slightly less than one standard deviation. So if we're looking for, we got 50% in the middle, that means we got a combined 50% in the tails. And since it's perfectly symmetric, we can divide that by 2. And we know that there's 0.25 in each tail. So we're trying to find these two scores. This time our goal is to find 2 scores. And I'm going to do it solely in the calculator, because I think that we'll probably end up using the calculator more than the tables as time goes by. So I'm trying to find that score. So first, if I go to inverse norm, the area that is to the left of that first score was 0.25. 25% was to the left of that. Now, this is where I'll go next, because this will give me my score. Now, notice this is it's not going to give me a z-score. It's going to give me a raw score. If I had 0 and 1 here, it would give me the z-score, and then I could use my formula for z equals x minus mu divided by sigma to find my IQ score. This is actually going to give me the IQ score. 25% is to the left of this score. The mean is 100. The standard deviation is 15. That means that IQ score is about 89.88. So we can find the other score. Now, may have to think a little bit. What was the percentage to the left of this score? It was 50 plus the 25, so it's actually 75%. Not 75, but 0.75. And again, this is going to give me the other score. So basically, the middle 50% of IQ scores are between 89.88 and 110.11. So 50% of people have an IQ score between those two scores.